Okay, so this week's vlog is going to be my test run of either one or both of the presentations I'm giving at IEEE this upcoming week. For this one in particular, be interesting is this is a little bit more on the relative harm index and where it all came from. So here we go, and we will be talking about wind applications in particular for this. This is part of the reason it was developed in the first place, and I can't talk about the Empower, but we start out with the empath looking at currents in the nacelle, and then we discovered that there were some other things going on. So we looked at higher frequencies because there were brushes being used on all the components in the tower, and there were a lot of specific issues, and we'll talk about that in a minute. But first we'll talk statistics, because I thought I had 15 minutes, turns out I have 30, so I thought I would put in the additional stuff. Right now, there is over 195,000 megawatts, that's 195 gigawatts of energy being, of basically wind energy, either built or in construction. 155 of that is online right now. 90,000 towers online or in construction. At the time that I put the slides together, there were 73,736 wind turbines online, which has been pretty stagnant. It's about 1,200 towers more than a year ago. We're actually seeing an acceleration of these, so there's more towers going up, and they're getting bigger. So it used to be that 52% of all the towers were GE 1.5 through 1.6 plus. Now it's GE 1.5s through 2.8s, and then they've got some larger ones coming on the market. Siemens, Vestas, and a few others are the primary ones. There's basically a top 10. Most of them are built or assembled in the US, and then of course they get assembled on site. They're all 1.5 megawatts or larger. The expected design life of a turbine is 25 years. So everything, all the statistics I'll talk about on reliability have to do with the expected life. Now at the end of 25 years or some time before that, there's the option to repower, meaning put in a larger generator, bigger controls, same tower. You might exchange the nacelle, but that means you don't have to pour more concrete, et cetera, et cetera, et cetera, and you can get a little bit more out of that site. So when we get into the actual defects, what's driving this kind of study is from 2012. Now, these statistics have gone way up, and I'll explain that in a second, but generators, 10% of failure. This is 2012, and at that time, basically, it didn't really scale up until 2003. So at this point, it's only 9 years in the industry. Generators, 10%, gearboxes, 5%, and main bearings, about 30% total. Well, what's happened now is in the life of a machine, now that we've had everything out for a little bit longer, and it's now 2025, you'll see usually at least one generator replacement. Gearboxes might be replaced once, and then main bearings might be replaced once or twice in a tower. And we're not discussing the blades. Blades may be replaced once or twice during the life of the machine due to wear and tear in the environment. So and of course lightning storms. Electrical discharge in particular across the life of the machines, and these are statistics from NREL, and these are more recent. Generator bearings are 25% of generator failures, and 60% of those are electrical discharge machining. Generator windings are 5% of the generator failures, and 30 to 50% of those are due to circulating currents, meaning problems with electrical discharge in the windings themselves. The gearbox, electrical discharge accounts for 76% of the bearing failures and 17% of the gear failures. Main bearings, and this is the primary reason we were doing the study, are 60%. Now, it also happens to be one of the more expensive condition. So in a generator replacement is usually starts at 120,000, and these are 2017 numbers. Average gearbox replacement is 500,000 or more. Specifically now it's about 800 plus. Average main bearing replacement is at least 800K, and none of that includes the lost production. Now you might have, if you lose a tower, they may not want to try to get a crane in or whatever else because it takes time. Now there's a few companies that do a crane up tower, which changes that. But you still have to wait for them as well as a normal crane. So normally when you would, bring in a crane by road, you would often wait until there's several towers. So you might be several months of not producing, and that could be anywhere from, that could be anywhere from, a few tens of dollars a megawatt hour to 800. I think we've surpassed $800 per megawatt hour a few times. Now, sometimes it goes into the negative. That's a different story altogether. But this is what drove the study. So one of the things that we went through and caught us off guard, because we'd always assumed that the part of the grounding system was to ground the nacelle. Turns out the nacelle actually floats. So we have a lot of circulating current up tower. And in a later slide, I'll show what the size of the conductor is for the ground. Now, the ground is there for lightning protection. So if there's a lightning strike, it provides a DC path. Ground fault protection, meaning if there's a severe fault, it does shunt it to ground. And then finally, personnel protection, meaning that you're protecting the personnel from being electrocuted by bringing them to the potential for that area. So you'll ground each part of the ladder. You'll ground different parts of the nacelle up tower. Now, there may be a lot of potential there, but you are basically grounded to that potential. Okay, so hard to create a touch point. Otherwise, some of the numbers we saw up tower on ground, well, they do not want those levels of currents passing through you. So when we did the initial study, now this later part is going to apply to industry as well. So there's a huge industry study that was completed at the same time. But we came up with, using the total harmonic distortion and total dynamic distortion, we're looking basically at THD for up to 50 orders on ground, not just the power system. So we did both, but on the grounding system. And what was particularly interesting was on the main bearings, which is this middle one here, we would see currents upwards of 150 amps, not milliamps, amps. Very rarely did we see anything under 10 amps. Usually it was 50 to 100 and some. Even on the generator, we would see high current, and then we measured across all the brushes and saw much lower current levels. So we went back later and we applied the Empower as well to look at the up to 22 kilohertz. Our discovery was to treat the super harmonics, that's the harmonics from 2 to 150 kilohertz. We right now have the only system for doing this type of work at 22 kilohertz. So we set up the relative harm index around 22 kilohertz. We're working on getting closer up here, but these clamps can only provide us data related to the 22 kilohertz. So in any case, what we discovered, because we do electrical and current signature analysis, is to go ahead and set it to set the line frequency current, whether it's ground or the machine, the peak in dB at 0, and then we have something that's relative to that value. So we looked at relative energy, and then we came up with what we called the relative harm index. So we collected the data. This is on the machine itself at a lighter load. So this is at the inverter, and of course lighter load. Like I said, you can see this. And this would be more of a square wave otherwise, but this is the inverter, and so this is the noise coming off the inverter. Well, that means that I don't have exactly 0 at any point, so that causes a common mode or circulating current. So the generator current, my peak is about 30 amps. Peak to peak would be a total of 60 amps. That's generator to ground. And then the main bearing ground, this is voltage, the green, it's very low value, but you can see here this particular one was at 150 amps. So what we did when we went ahead and treated it as, what we do in current signature analysis, you'd see this value up here. This is a lot of noise. Usually the ground floor is near 100 dB down. It's way up here, so there's a lot of peaks going on inside this area. But once we get this, then we can look at the different frequencies. Now, if I have brushes on here, a majority of that current is going to flow through the brush under 10 kilohertz. But as we increase, we cross some lines. So you'll see that. I'll show you that in a second. But current in decibels, 20 log 10 of the current divided by the peak current. So the current at whatever frequency divided by the peak, that's what gives us these decibels. The relative energy involved would be squaring that, and then the relative harm is to look at that, and it could be, less than 1 time or more than 100 times. We'll take a look at that. N is the actual index. So the current through the bearing, now this you have to keep in mind is basically if I have a shaft brush there, it does not mean that I have 100% of the current flowing through the brush. So I can get some estimates. This also means I don't have to take direct shaft current readings, which was great because you can't be up tower when you're taking data. So we had it set up so it would collect data while personnel were down off the nacelle. So when we got the data, when we got the information in, you look at the current, so the current of the bearing, so total current on ground, multiplied by the impedance of the brush divided by the impedance of the bearing plus the impedance of the brush, determines how much current is passing through the bearing. The relative harm index, we went back and we got all of our data based on this, and then that was up to 10 kilohertz before, up to 6 kilohertz before, and then more recently in the last year, we've been able to do the 10 through 22 kilohertz using the Empower system. So this is your dB level, and this is the frequency. So you can see 60 hertz is going to be 0. So, but as my dB level is down, and this is not just harmonic, but intra-harmonics at the supraharmonic range. Yeah, a lot of supra and intra. That gives me the ability to say caution. Blue turns up better than green, so use blue here, so that's good. And then as I come here, this is the worst. So 22 kilohertz, if it is at 0, that means I have a severe issue. If I'm down and I'm at the base noise floor, you could see that I don't have a lot of conditions to worry about. So negative number good, positive number bad. And this is what I'm talking about. So when I take a look at it, what's happening is my brush impedance, so this would be the bearing, so relatively high impedance. Now, these are numbers using an oil film, no contaminants or anything else, so it varies a little bit, and it's off a specific common bearing up tower, but this was the calculated impedance value for the bearing. So you can see that the impedance of the bearing decreases pretty rapidly as the frequency goes up. These should be a little flatter and then curve up, so it looks a little sharper, but this is the way the graph came out. So the silver is here. They tried also a couple other materials, and those were about the same. They fell between the orange and the green, and you can see that at certain points they cross each other, meaning that the bearing is going to be carrying more current than the brushes. So if I say do 100 amps on ground, this is these here would be the currents that the bearing is carrying. So once I start looking at that in amps, once I start looking at that, I can come over here and determine the severity. Like, okay, so if it's less than 10 amps crossing through the bearing, it's long-term wear, etc., etc. So the better material I use for a brush, the less current that's going to flow through the bearing. And we're also looking into some other solutions as well. To put it into perspective, this is the ground for a tower. So you consider that this particular tower can carry 2,500 amps. Each of these 3 thicker cables is a phase. So this is lightning protection. Again, this is the same thing, a ground for the tower tied to the base. And then there's, of course, the ground grid. That's to put it in perspective. So obviously, we're primarily circulating currents up tower and a few other things. So if there are any questions at this point, please ask. And this would be what I ask in the presentation. I only got 16 minutes out of it, so that means that I'm going to have to slow my pace a little bit and then give them about 10 minutes of questions. But this should be a good intro to the relative harm index, and for those watching this that want to apply it in industrial applications, which is basically what it's set up for. So the Empower system has a 44 kilohertz sample rate, Nyquist of 2. That gives us that 22 kilohertz. I can boost it out a little bit if I need to, but these are solid. These are all a lot of noise that's going on because this is ground. And then you can see here, if I don't have a brush, at 5 kilohertz, I'm at about 18. 10 kilohertz, I'm at about 30. So let's go off of these two here. 20 kilohertz, I'm at about just a little bit more than 40 dB down. So let's take a look at 18 dB down at 5 kilohertz. So that would be somewhere in between these two. 18 dB down at 5 kilohertz is going to be somewhere about 100 times more harmful than if there was no shaft current. And then let's go out here to 10 kilohertz, and that's 30 dB down. So 10 kilohertz at 30 dB down. Okay, so 1.5, and then the 40 kilohertz at about 20 kilohertz. That's going to be, again, over 1. So I have to mitigate the issue. Now, once I know what the current value is, then, so if I'm looking at a couple of amps on ground, then that means that it will eventually start fluting or getting some surface contamination, basically some fuzziness on the reflective surfaces. So with that, that's kind of what I'll be presenting next week. There is a paper associated with it. I will have that up at some point in time. But if you have any questions, reach out to me at MotorDoc LLC. Right now, the Empower is the only device that can detect the supraharmonics in both industrial and utility applications until you take a big jump up to one that's being used for the grid. And then we're looking at other portable equipment as well. Now, the Empower is a small portable device that you can hold in the palm of your hand, and then a current clamp along with your PC. So if you have any questions, like I said, reach out, info@motordoc.com. I'll have it at the end. Thank you very much.